This is Anthony Priscilla wrapping up our discussion on zeros of polynomials today. We're working with possible rational zeros, finding all the possible rational zeros for our polynomial. And we had said that all the possible rational zeros are in the form plus minus factor of the constant term. Now the constant term, remember, that's the term in the polynomial that doesn't have a variable on it. Like we had done number 11, and the constant term is 8. That's a number that doesn't have a variable on it. Notice I didn't bother with the minus. We'll take care of that later. And then over factor of the leading coefficient. The leading coefficient is that first coefficient when it's written with the exponents in descending order. If it's not written in descending order, it's the one that has the biggest exponent. The coefficient on the term that has the biggest exponent. I think most of them in this assignment are all in descending order. So it's all in the form factor of the constant term over factor of the leading coefficient, plus minus. So once you write out those factors, you go 1 over 1, 1 over 2, 2 over 1. Now 2 over 2 is 1, we've done it. 4 over 1 is 4, 4 over 2 we've listed. 8 over 1 is 8, 8 over 2 is 4. So we got 10 possible rational zeros. There can't be that many. There should only be 3 zeros, but here are the only possible rational ones. And so you can either do synthetic division or just plug in until you find 3 of them that give you 0. If you find 1 of them, then you can do synthetic division the way we did on some of the other problems. But finishing up this exercise, problem number 12. You go factors of the constant term. Oops, paper's crooked. Factors of 27. Let's see. 1, 3, 9, 27. And then factors of 3, that's the leading coefficient. Then you go plus minus 1 over 1, 1 over 3, 3 over 1. 3 over 3, we've already done that. It's a 1. I'm taking each one of these numbers, putting it over there. 1 over 1, 1 over 3, 3 over 1, 3 over 3 is 1, okay. 9 over 1, 9 over 3 is 3. 27 over 1, 27. 27 over 3, we've already done it. Sometimes students start thinking you're going big number over small number. No, it's a factor of that constant term. It's not no big number and small number. Maybe it just so happens that the constant term is the biggest number. On number 13 we have, let's see, 18 is our constant term. So factors of 18. 1, 2, 3, 6, 9, 18. Factors of 2, just 1 and 2. So 1 over 1, 1 over 2, 2 over 1, 2 over 2, 3 over 1, 3 over 2, 6 over 1, 6 over 2 is 3, okay. 9 over 1, 9 over 2, 18 over 1, 18 over 2 is 9. Hey, let me see, I haven't been looking. Let's see. Is this it? 1, 1/2, 2, 3, 3/2. Yeah. What about this one up here? 1, 1/3. 3, 9, 27, that's D. Oh, this one's going to be pretty easy, isn't it? The constant term is 24. So 1, 2, 3, 4, 5 doesn't divide into it, 6, 8, 12, 24, let's see, 1 times 24, 2 times 12, 3 times 8, 4 times 6, that's it. Now factors of 1, see what I'm saying, it's going to be pretty nice, it's just plus minus all of those numbers. Let me do it the lazy teacher way. I'll just look here. No, it's not that one. 1, 2, 3, 4, 6. This is it. C. Okay. And one left to go. Let's. So that's. Oh wow! Factor. The constant term is 23. Not a lot of numbers multiply together to give 23. That's prime. When I say numbers, of course, I'm meaning integers. 1 over 1, 1 over 2, oops, 23 over 1, and 23 over 2. So that's this one right here, D, I believe. There. So I think that wraps it all up, because now once you know these, here's the 2, 4, 6, 8. Only 8 possible rational numbers that you could plug in and give 0. So just plug them in, or do synthetic division till you get a remainder of 0. And once you've done that, you'll be down to a quadratic equation that you can either factor or use the quadratic formula on, which we did on some of the another problem before we began this. Okay? So that's it. Again, this is Anthony Priscilla with my college algebra class. Bye-bye.